Welcome to Summarize Science. Today, we're diving into a fascinating paper that tackles one of the biggest challenges in space exploration. How do you hit a target over 4 light-years away? The mission in question is similar to proposals like Breakthrough Starshot. The idea is to send a tiny, gram-scale spacecraft to Proxima Centauri b, our nearest exoplanet. Propelled by powerful lasers, this probe would travel at 20% the speed of light, making the journey in just over 20 years. But over such a mind-boggling distance, even the smallest nudge can send it wildly off course. Researchers behind this paper wanted to figure out just how much of an effect gravity from different celestial bodies would have on the probe's trajectory. They also wanted to know if we need to use Einstein's theory of general relativity, or if good old Newtonian physics is enough. Using a highly advanced computer simulation, they modeled the journey, including the gravitational pull of the Sun, Earth, Jupiter, and even the destination star system. The first major finding, shown here in Table 1, is that our own Sun has the single greatest gravitational influence on the spacecraft's path. That might seem obvious, but it's the scale of the effect that's important. And this leads to the next crucial point: Newtonian physics is not good enough for this job. As you can see in Table 3, if mission planners calculated the trajectory using only Newton's laws, the spacecraft would miss Proxima Centauri b by about 690,000 kilometers. That's a massive miss, nearly double the distance from the Earth to the Moon. Relativistic effects, which kick in at such high speeds, are absolutely essential to account for. The good news is that the researchers' simulation, which includes these relativistic effects, is incredibly precise. They showed that they could fine-tune the initial launch velocity to calculate a trajectory that hits the target with femtometer accuracy within their model. That's smaller than the nucleus of an atom. But here's the twist, and it's the most important takeaway from the study. The biggest source of error isn't complex gravity or relativity. It's the initial launch. The paper shows that a tiny, almost infinitesimal error in the launch angle can lead to a colossal missed distance. Looking at Table 4, a launch angle variation of just 100,000th of a degree results in a miss of nearly 5 million kilometers. This error from the initial boost phase completely dwarfs the errors from gravitational calculations. Interestingly, the researchers did find that gravity offers a tiny bit of help. As the probe nears its destination, the gravity from Proxima Centauri provides a slight focusing effect, pulling the spacecraft toward the target and reducing the final missed distance by a small amount. So, let's recap the key points. First, any future interstellar mission traveling at relativistic speeds must use general relativity for course plotting. Newtonian physics alone will lead to a massive failure. Second, while gravitational models can be made extremely precise, the real make-or-break challenge is the engineering of the launch system. The ability to aim the initial laser boost with near-perfect accuracy will be the single most critical factor for success. This research highlights that getting to the stars isn't just about going fast, it's about starting the journey with an almost impossible level of precision. Thanks for watching Summarize Science.